In this presentation, I am going to explain stator voltage and frequency control of induction motor drive. How the uh, speed of an induction motor can be controlled by controlling the stator voltage and frequency. Coming to stator voltage control of induction motor drive. As you know, the torque of an induction motor is proportional to the square of voltage, or torque is equal to 3 by omega s into v squared by rr dash divided by s into rr dash plus rs whole squared plus xr dash plus xs whole square, or basically torque is proportional to the square of the voltage. By controlling the stator voltage, the torque or thereby the speed of the motor can be controlled. The plot represents the variation of developed torque T versus speed. As the voltage is equal to V1, it is above both V2 and it is again above V3. Or as the voltage is reducing, the torque speed characteristic shift downwards. And there is another low torque is there. And the speed at which it is running is decided by the point of intersection of the motor torque and the load torque. Therefore, corresponding to a voltage of V1, it is running at a omega 1, and corresponding to V2, it is omega 2, and corresponding to a voltage V3, it is equal to omega 3. Since the voltage V3 is less than V2, which is less than V1, we can say that the speed omega 3 is less than omega 2, which is less than omega 1. Therefore, by reducing the voltage, stator voltage, you can reduce the speed of the motor. Therefore, the voltage is varied until the motor torque is equal to the load torque. Therefore, the stator voltage control method is suitable for the applications where load torque decreases with the speed. As an example, a fan load. In the case of fan load, this type of voltage control can be used. This method gives a speed control only below the normal rated speed, as the operation for the voltage, if higher than the rated voltage, is not admissible. Therefore, you can control the speed of the motor less than the base speed or the speed corresponding to the rated voltage by this method. Continuing stator voltage control of induction motor, you can see that as the voltage changes, though the curve is shifting, the slip at which the maximum torque remains same and maximum torque is reducing, or the maximum torque is equal to 3 by 2 omega s v squared divided by xs plus xr dash. Therefore, if stator resistance Rs is neglected, therefore, if the voltage is reduced by 80%, the maximum torque is reduced by 64%. So, how you can control this stator voltage? How can you get the variable stator voltage? That can be done by using a circuit like in each phase there will be two SCRs back to back connected. Therefore, by controlling the firing angle of this anti-parallel connected invert SCRs, the value of the stator voltage can be varied, and thereby the speed of the induction motor can be varied. Therefore, by controlling the firing angle of the SCRs which are connected in anti-parallel in each phase, you can vary the fundamental voltage applied to the stator. And by always thing is that this stator voltage speed control is possible, can be done only for the speed less than the rated speed. Now in this slide I am going to explain what are the different methods for obtaining a variable output voltage from an inverter. We are using an inverter. It can be either 6-step inverter or PWM inverter. Now if the input is a DC voltage, we will be connecting a chopper at the front end side. By controlling the duty ratio of the chopper, you will be getting a variable DC voltage at the input of the 6-step inverter. Therefore, by varying the input voltage here, you can vary the output voltage. Fundamental output voltage available at the stator voltage, stator of the induction motor can be changed by controlling the duty ratio of the chopper, provided the input is a DC source. Instead of a DC source, if the input is a three-phase AC source, instead of that one, at the front end will be connecting a control rectifier is connected. By controlling the firing angle of the control rectifier, you can vary the DC input voltage to the 6-step inverter. Therefore, the control rectifier output, there's an LC filter is there to get a constant voltage at the input of the 6-step inverter. By controlling the firing angle of the control rectifier, you can vary the DC input voltage to the 6-step inverter, and thereby you can vary the fundamental output voltage available at the stator of the induction motor. Therefore, by these two methods, either by using a chopper if input is a DC voltage, or by using a control rectifier if it is an AC input voltage, you can vary the either firing angle or the duty ratio. Thereby you can vary the DC input voltage to the input to the inverter, and thereby you can vary the fundamental AC output voltage that is available at the stator of the induction motor. Therefore, if the input voltage is a constant AC, variable DC voltage at the input of the inverter can be obtained by controlling the firing angle of the rectifier at the front end, which is connected at the front end as shown in the figure. Now let us see what are the different methods for obtaining a variable output voltage from an inverter. Now, unlike the previous explained 6-step inverter, you can use PWM inverter, pulse width modulation, sine PWM inverter. Now, first at the front end, there will be a uncontrolled rectifier, that's a diode rectifier, and input is a three-phase AC input is given, and there's a filter, LC filter is given, and at the input of the inverter, you are getting a fixed DC. Therefore, inverter input is a fixed DC, and that is given to a PWM inverter, and output of this inverter is connected to the stator of a induction motor. Now let us see how the voltage of this stator voltage can be controlled by using a PWM inverter. Pulse width modulation, sine PWM, there are two control signal. One we call it as modulating signal, that is a low frequency sinusoidal signal, and that's also called reference signal. Second is the high frequency carrier signal is there. Normally that will be a triangular signal. Therefore, these two signals are being compared. High frequency carrier signal is being compared with a low frequency modulating signal using a comparator, and that comparator output is used to trigger or to control the switches in each leg, and switching signal to the bottom of that leg will be the just complement what the given to the top. Therefore, by controlling in a sine PWM fashion, you will be getting the fundamental output voltage will be sinusoidal, and that will be in phase to the modulating signal. The fundamental output voltage of a sine PWM inverter will be in phase to the modulating signal. Now, the magnitude of the fundamental output voltage, that is given by MA into VDC. Now, to see this one, there are two indexes to explain that one. One we call it as amplitude modulation index, another one is called frequency modulation index. Amplitude modulation index is the ratio of the maximum magnitude of this modulating signal or this reference signal divided by the maximum magnitude of this reference, this carrier signal, triangular signal. The ratio of these two one we call it as amplitude modulation index, MA. Another thing is that frequency modulation index, MF. MF is the ratio of the carrier signal, triangular signal, to the frequency of the modulating signal. That is what we call it as MF or frequency modulation index. Now, by controlling the value of MA, amplitude modulation index, you can vary the fundamental output voltage of the inverter. For the fundamental output voltage of the inverter, which is connected to the stator of the induction motor, that is given, the maximum magnitude is given by VL1 equal to MA into VDC. Therefore, the RMS value of this voltage is given by MA into VDC divided by root 2, or that is equal to 0.707 VDC. Therefore, by controlling the modulation index MA, you can vary the fundamental input voltage to the stator of the induction motor. Now, to vary the frequency, this one, the frequency, fundamental frequency is same as the frequency of the modulating signal. Therefore, by controlling or by varying the frequency modulation index MF, you can vary the fundamental frequency. Therefore, by varying the amplitude modulation MA, you can vary the fundamental output voltage magnitude, and by controlling the MF, you can vary the fundamental frequency output of the inverter, which is given to the stator of the induction motor. The advantage of PWM sine PWM inverter is that there is, unlike the previous case, 6-step inverter. In 6-step inverter, there will be lower order harmonics as there, and that will be causing heating in the machine. That will be producing a reverse torque. That is not the efficiency of the induction motor. More losses are the efficiency is motor is less. But in sine PWM case, these low frequency are not there. All the harmonics are centered at high frequency, 2 mF plus or minus 1, like in that range it is centered. Therefore, it is very easy to filter out this high frequency harmonics by using a small value of inductance, or even the stator inductance will do that one. Therefore, the advantage of sine PWM is that harmonics are centered at high frequency that can easily be removed. Therefore, in stator voltage control of induction motor, the stator voltage can be controlled by controlling the PWM inverter. In sine PWM inverter, that can be done by varying the amplitude modulation index MA, or by varying the magnitude of the modulating signal. And similarly, in frequency control, that is, next we'll see that V by F control, like everything. In that case, you can change the fundamental frequency by changing the frequency of the modulating signal, or by changing the modulation index MF. Now we are next part of this one, I'll be explaining what is the frequency control. Frequency control of the induction motor.